let's go ahead and finish the problem we started yesterday. We did do part A was just the free body diagram. Part BI was essentially proving Kepler's third law, right? We talked about that. In answering the question, we did so. And one thing I wanted to point out, we'll talk about that in a second. And BII, the second spacecraft of mass 2m is put there, and we did answer that question, right? And the answer was that it'll have the same, everything's the same, because the mass of the thing doing the orbiting doesn't matter. It could be the mass of a spacecraft, it could be the mass of a grain of sand, they will have the same orbital speed. How do I know that? They cross out, they cancel out of the equation, therefore they have no bearing on the outcome. Alright. C is tricky. The first spacecraft is moved into a new circular orbit that has a radius greater than r. So it's increased its orbital altitude. Is the speed of the spacecraft in the new orbit greater than, less than, or equal to the original speed? Don't say yet. The answer to this question is pretty simple, or at least if you know what's going on, if you understand the equations, it's pretty simple. The engineering to make this happen is not. The engineering, when we come up with the answer here, we got to conceptualize, well, how would they actually make that happen in reality? You know, it would be easier than taking a spacecraft from here and going into orbit, a higher orbit. It'd be easier to just take that spacecraft, fire the rockets, and get to escape velocity and leave and never come back. That would be easier to do from an engineering standpoint than taking this guy and changing the orbit. Okay? And you'll see why in a second. It's not, I wouldn't say it's easier. It's less complicated. It's a less complicated process of getting someone from orbit out of the solar system than it is from getting orbit to a new orbit. The physics equations aren't that bad, but the engineering, the actual making it happen is kind of tricky. So anyway, how do we answer this question? Is the speed of the spacecraft at the new orbit greater than, less than, or equal to the original speed? What do you guys think? Greater? Greater? Less?
Are you assuming like the time is still like the time it takes to go around one orbit is the same?
Well, think about that. If these guys are orbiting in the same amount of time, this guy would have to be going faster. Yeah. But we're not assuming that. Oh. There's nothing about the question that says they're going to go around the same amount of time. Right? So let's look at this and maybe get a visual. Oh, not that one.
And help ensure that it doesn't break things.
Here we go.
Non-imaginary one.
So here I got three objects orbiting at different distances. I got a little blue guy, a big green one, and a little white one right there. And I will show the velocities. Velocities, view velocities, show values. Bigger arrows. Spoiler. Objects that are farther away move slower. Because the gravitational force as you move farther away gets weaker. Therefore, the centripetal acceleration it creates gets weaker, smaller. Therefore, you got a smaller speed. Okay. So that's what's tricky. You got to be moving slower here than you are here. But you can't get to that higher orbit unless you fire your rockets. So what actually has to be done is you got to start firing your rockets so that you start, traveling in a larger elliptical orbit temporarily. And then once you start getting close to that orbit, you actually have to flip the space shuttle around and then fire the rockets so you actually start slowing down to that final speed that you want at that orbit. And then finally when you get there, you got to flip back over. And then now you're in the orbit of that new thing. And it's a complicated maneuver. They don't do it that often because there's really not much point in changing orbital elevations. But if you wanted to do it, that's what you'd have to do. It's a very complicated maneuver. The equations are easy to understand, though. You have to be moving slower there, right? And we can prove that with equations. And this question says, is the speed of the spacecraft in the new orbit greater than blah, 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 blah. And then briefly explain your reasoning. Well, I feel like the reasoning is most easiest to explain whenever we... Let me be specific here. Go to new orbital distance. Yeah. So we want to relate the speed, because we're asked is it going faster or slower when we're at our new orbital distance. Well, we can do what we've already done a few times and use the two equations that we now have for the gravitational force on an object in a circular orbit, which are Newton's law of universal gravitation, which in this case is G times the mass of the Earth times the mass of the satellite, which is just M, or the shuttle, whatever it is, over the orbital radius squared. And then we also know that that is equal to the mass times acceleration, where the mass, and I'll do mass times centripetal acceleration. In the second one, right? If this is the only force, then it's equal to ma as well. So ma, and it's also equal to this. Everyone brought the mass of the shuttle to the party, so it goes away. And I can write G times the mass of the Earth over r squared. And then we make the substitution that we do 99.9% of the time. Centripetal acceleration is speed squared over the radius, orbital radius. Do that on the right side for centripetal acceleration, and we get that. We've already done this a few times. That's why I'm going kind of quickly. One r from each side goes away, and then square root both sides, and I get that the orbital velocity for a circular orbit is equal to the square root of big G, mass of the Earth, over r. So, and again, it's understanding the equations that indicates the knowledge of the physics. So, if this tells you the answer, this tells you the answer because I know that the orbital velocity is inversely proportional to the square root of the orbital distance. Right? Think of it this way. If I increase r, what's going to happen to the orbital speed? Decrease. It has to decrease. R is in the denominator. Yes, it's under a root symbol, but it's under a root symbol in the denominator. So if it increases, this guy's got to decrease. So your bigger orbital distance, the farther you are away, the slower you're going to go. Sound good?
So
what's that?
I was going to say, is the ones in the numerator in the orbit, or the velocity of the orbit, those are just directly proportional?
Mm-hmm. Okay. Mm-hmm. So let's have this discussion. The orbital velocity is directly proportional to the square root of the mass of whatever's being orbited. You don't say it's proportional to G because G is literally the proportionality constant for all this. It is just a number. But yeah, so I could go off to the side and say V orbit, if I just want to talk about proportions, it's proportional to the square root of the mass of, in this case it's the Earth, but in the context of whatever's being orbited. And the orbital velocity is also inversely proportional to the square root of r. Now this carries an interesting implication. If let's say I have an orbital speed, orbital distance, and I want to increase that orbital distance by a factor of 4. So I want to go from r to 4r. How is my velocity going to be affected by that? Can anyone tell me? It's going to decrease by half. It's going to be cut in half. Right. We'll talk about why. If that's not obvious, we'll talk about why, because I'm going to show you how to. That's kind of a typical kind of problem that is going to start popping up more frequently now. Once we do this and then get into our unit on energy. So I'll talk about that today. All right, so the equation says, and how would I answer this? Because it said justify the answer. Well, first of all, we've generated, I think we've gotten this equation elsewhere in the problem. Did we? Maybe we didn't. Anyway, you can say this equation, and you can say, like if I was answering this, I would say, obviously it's smaller. It's going to be smaller velocity. To justify that, I just say that the orbital velocity is inversely proportional to the square root of the orbital distance. So as r increases, v must decrease. And that's full points right there. You can word that however you want, but something like that. So let's look at the scoring guidelines real quick, and then I'll show you another example problem, and then we got an MCQ assignment that I want us to work on. This, by the way, I told you that I was going to have you submit it. Don't worry about submitting this. Just keep it with you for reference. All right. So yesterday, if you were following along, which you hopefully were, Part A, 1 point is earned for an arrow direct. Remember, this was just the free body diagram here, right? Is an arrow pointing that way, and is a gravitational force. That's all you had to do there. That's literally it. And got you 2 points. 1 point for an arrow directed toward the Earth's center. The second point a correct label on the arrow representing the gravitational force. Note a maximum of 1 point may be earned if extraneous forces are present, meaning you could have got these two, but if you put another vector on that, you've lost one of those points. Now keep in mind, this is a very common mistake that people make, especially like when they're fresh off of the centripetal motion unit in introductory physics. And that is this. If you were to do this, answer this question thusly, you would only get one of those 2 points. So don't do this. This is a silly reason to lose points. If I do that, I only get 1 point. If I do this, I get both points. What's the difference? This is telling me what force is acting. Right? This is telling me exactly what's going on. Not what's going on, but this is telling me the forces that are acting on the object. It's not actually telling me, my free body diagram doesn't tell me exactly what's happening. Because if this guy's not moving, this force tells me that the thing is falling straight into the earth. But if it's moving, it's not. So free body diagrams aren't designed to show you what is happening. They're designed to show you what forces are acting and in what direction, and that is it. That is it. That's all they're used for. If I do this, I'm not telling you, if you're looking at this, what the force is. I'm telling you what the force is doing. I'm telling you what is happening, right? That's not. Any force can be a centripetal force, right? If I draw a diagram like this, and I say this guy's moving in a circle, and he has, because it's like this, and I label that like that, no one looking at that has any idea what I'm talking about. It's just some object moving in a circle. It could be an object, a ball on the end of a string. It could be a giant planet or a giant star orbiting a supermassive black hole. I have no idea. So you have to say, all right, well, put that a G. That's telling me now, okay, that's a gravitational force. That's all I need to know. Right. Again, never label a force as a centripetal force. You want the grader of your AP exam to know exactly what type of force is acting. That's what a free body diagram is for. Which is why I like always starting from the standpoint of Newton's second law, writing the equation first, then putting the C's for centripetal, and then in the next step, in this case, it's going to be a gravitational force. And again, that I get from my free body diagram. All right. That's 2 points. I think there's only like 7 points total for this one, or something like that. There's a significant portion of the points for this entire FRQ came from that, drawing that arrow and labeling it correctly. Number B, there's two parts. The first one, derive that equation. Deriving Kepler's third law. Guess how many points you get for that? 3. Part I, 3 points are earned. So all that work that we did, all the algebra that we used to end up with essentially proving Kepler's third law, 1 extra point as compared to drawing a free body diagram, drawing an arrow and labeling it. Hence the point that I made yesterday. If you find yourself spending 20 minutes just doing algebra and you're going around in circles, the vast majority of the time you are sacrificing points. You are missing points that you would have gotten elsewhere to focus on trying to get 1 point or 2 points that you might not even get anyway. So if you find yourself just doing a whole lot of algebra and you don't feel like you're getting anywhere, just hold off. Put a pin in that. If you have time at the end, come back to it. If you don't worry about it. There's only so much, worry about it if you really need the grade and score, but there's nothing you can do at that point. Excuse me. So how are those 3 points earned? What happened? Why is it written like that? It's so weird. It wasn't written like that second period. Huh. Anyway, 1 point is earned for using or implying Newton's second law and equating the centripetal force to the gravitational force. So this is what we did. This is equating this, either in that form or this form. Equating that with, the force of gravity expressed as big G m Earth m over orbital distance squared. That's one of the points was from just realizing that those two expressions are the same. And notice it says or implying, for using or implying, right? You can skip the initial steps as long as the reader sees that you have something that shows that those two forces are equal to each other. What's that? It's not for you. Matthew Burner. It says, it says they're retroactively giving you 3 Fs in classes from 3 years ago. That's probably going to affect your GPA.
Who's taking over the goal? Let's go.
Alright. The next point for explicitly or implicitly determining the speed of the spacecraft is v equals 2 pi r over the period. So that means whoever's grading your paper is looking for this at some point. Somewhere in the work, they see 2 pi r over the period, which means the expression for speed that we have here, right? Bless you. Bless you. And then the third one for a correct answer, algebraically equivalent to, the way I wrote it was the period squared equals, what is it?
4 pi squared r cubed
Over GME
Yeah.
times r cubed.
Yeah.
Okay. Okay. So that's for the third point, just coming up with that. They notice they said it t equals the square root of that, or just t squared equals that, whatever. Anyway, written like that. Yeah. So that's the third point. Part 2 was just when you put mass 2m there. What about its orbital speed? And the correct answer was same. That one's only worth 1 point. 1 point for part 2.
Wait, you can leave it as t squared?
Yeah. I mean that's what Kepler's third law stated. Kepler's third law states that the square of the orbital period is proportional to the cube of the orbital radius.
Which question is part 2?
What's that?
Which question is part 2?
Wait, say what?
Which question is part 2?
What do you mean which question was part 2?
Yeah, like what was the question?
like part.
Oh, the question, it was you replace the mass m with the mass 2m, and how is that going to affect the orbital speed at that height, or that altitude? And the correct answer is, well, it's going to have the equal speed. Note, for an incorrect answer consistent with part B, the explanation is still graded for consistency with part BI. Meaning that in part BI, you might have lost a point by coming up with the wrong answer, but if your answer to the next part is consistent with it, then they actually don't take off credit, because they understand that while you made a mistake, you are making the right conclusion from that incorrect previous answer. Anyway, so that was an easy one. And then number 3. Again, 3 points for all that algebra. 2 points for drawing an arrow and labeling it correctly. Okay, keep that in mind when you find yourself doing a bunch of algebra on an FRQ, either on a test in this class or on the actual AP exam itself. All right, and then the part C, that was where if you go to a new orbital altitude that's higher, are you going to be moving faster or slower? Is your velocity greater than or less than, and just less than? Notice only 1 point for that. For a correct, 1 point is earned for a correct explanation as to why the speed decreases. So obviously, if you say it increases or it stays the same, you're wrong. And if you mark less than and you don't justify it, you're wrong. You don't get this point unless you've obviously got it right and then justified the obviously right answer. All right? So that's how those scoring guidelines would go. All right, now we do have don't get started on it now because I'm going to show you an example problem or two. I have an MCQ AP classroom assignment, and I have made sure that there are a few, it's not that long, it's 7 multiple choice questions, so don't think it's going to be long. There are a few of them that kind of illustrate a type of problem that I've talked about before, but that we're going to start seeing a lot more of. And so let me just give you an example of this type of a problem. Before we do that, let me point something out about this. Remember when Kepler did his thing, he was talking about the sun and things just orbiting the sun. So for Kepler, it was this. The period of a planet squared, an orbital period of a planet squared, is equal to all this junk. This is all constant, right? So this is one constant number. It has a single numerical value. It is a constant. And so it equals that constant times the cube of the orbital radius. Do you think Kepler knew what the mass of the sun was? No. This was long before Cavendish. You couldn't figure out the mass of the sun until you knew what big G was. Big G wasn't discovered until the 1800s, Kepler 1500s. So it was a long time. There's no way. In fact, he wasn't even considering the value for big G. He just knew that this guy was proportional to that guy, and this is some proportionality constant. It wasn't until Newton came along that we actually discovered what that proportionality constant breaks down to. And it's a combination of, obviously, 4 pi squared, big G, and the mass of the star. So how is this useful for Kepler? Well, Kepler was clever, and he understood ratios, okay? And the problems that the example problem I'll show you today is a ratio. You can solve it using a ratio method, some people like to say it. I don't like calling things methods because then it feels like I got to memorize a bunch of different approaches to problems. But let me just divide both sides by r cubed here. Because when I do that, I get this. And let's say I'm doing it for the Earth. So the ratio of the square of the orbital period to the cube of the orbital radius for the Earth is this, which is a constant for the solar system. So what that also means is that, what's your favorite planet, Taylor? That we can see in the night sky with our naked eyes? Venus. This is also the ratio of the square of the orbital period for Venus to the cube of the orbital radius for Venus, right? Because you could do the same calculation for Venus, or for the Earth, or for Pluto, or for Neptune, or for an asteroid, or in the asteroid belt, or for a comet out in the Oort cloud. And if it's orbiting the mass of the sun, then these will always be true, which means we can just bypass the middleman and compare these ratios for objects that are orbiting the same thing. Right? And what's nice is that whatever units you decide to use for these things is just your results are going to be expressed in the same unit. So it's often easy to say, well, the orbital period for the Earth is 1 year. The orbital radius for the Earth is 93 million miles, but we don't want to use that. We just want to use 1 astronomical unit. So if we say, so that's 1 squared over 1 cubed, the left side is just 1. We measure how long it takes Venus to go around the sun. Say, we just measure how long it takes. We get a number for that, right? In the Earth years. And then that will allow us to calculate how far Venus is from the sun in astronomical units, which is what we call the distance from the sun to the Earth. Just call that 1 astronomical unit. And then I can see what fraction of our distance will Venus be at. So you don't even need this. All you have to do is to figure out how far Venus is from the sun, is measure how long it takes to go around the sun. That's literally all you need. With Kepler's third law, we can figure out how far away Venus is without knowing the mass of the sun, without knowing G. That is the power of analyzing physics using ratios. When you do ratios that are equivalent to a constant, you can bypass the whole constant thing. Okay? All right. So let's see that same effect, but in a typical style of problem. And if you have friends in second period, tell them I'm sorry, because I messed up second period. I messed up bad. I blame. Who I blame? Alonzo. Blame Alonzo.
I would blame Nolan.
Yeah.
He
I blame
taught me a
Nolan.
lot, right?
Yeah. Wait, no, it doesn't. Okay. So the example, I forgot to print it out, so you just have to write it down with me. So let's say a planet let's say we start on the Earth, okay? So here's the Earth, mass Earth, and we have a satellite of mass ms orbiting the Earth. And so we know it's going to be moving. Let's say it's moving down here. That's its speed, and so it's going to be moving in a circle. It's going to feel that gravitational force, obviously. Okay. And so the question might say something like, a shuttle is in orbit around the Earth at an at a distance r. So I'm just going to call it r, the orbital distance, not radius of the Earth, just total orbital distance r. If the mass of the Earth was, what do you think, tripled, quadrupled, doubled, which one?
Quadruple.
Quadrupled. What's quadrupled? And R remained the same. What would happen to V? And when I say what might happen to V, we're not actually going to get a numerical answer for this, but we're going to get an answer as a fraction, an answer in terms of our original speed. So a shuttle is in orbit around the Earth or any other planet, it doesn't have to be Earth, at a distance r. If the mass of the Earth was quadrupled and r remained the same, what would happen to V? Intuitively, what do you think would happen? Would it speed up, slow down, or stay the same speed? If the mass of the Earth suddenly increased by a factor of 4. It's going to speed up, right? Gravity's pulling on it harder now. Gravity just got a lot stronger. So you got to be moving a lot faster to avoid being pulled down as you're moving, right? So yeah. All right. So this is, it doesn't seem like this is some special typical kind of problem. It just seems like, okay, this is specific to this unit. But this is a style of problem that is very common in physics, more so in College Board AP physics than in just normal college physics problem sets, I've noticed. And what essentially it boils down to is this. The problem starts with a given situation. I got a mass ms in orbit around a mass me at a orbital distance r. And then the situation gets modified. In this particular problem, the modification, the mass of the Earth is quadrupled. R could change, but it's not in this case. Do you want R to change? Do you want to make it that complicated? Do you want to make it more like the problems that you're going to have to do on the assignment?
Yes.
Okay. So R, what do you think? Tripled. So R is tripled. What do you say? I'm telling you, this is easier than you're going to think. I'm telling you. So the situation got modified. Not only did I change, now it's not so straightforward. Well, is it going to be going the same speed? Smaller speed? Yeah, it's good that we did this because I'm not really sure. So what do we have to do? We got to figure it out, right? It's obvious in the way. If the mass Earth gets bigger and I'm at the same distance, I got to go faster. But if the mass of the Earth gets bigger, but then I also move away from it, then I don't know. We got to see. So that's the modification of the situation, right? It always looks like this. So you're given a situation and it says, okay, well now if this thing happened, or this thing was increased or decreased by this amount, and this thing was increased or decreased by this amount, what effect would it have on this other thing? Okay? And so that's what happened. The last part of here, the question is asked. And it's always how is one thing affected by the changes that you've made. Okay? So how do we set this up? There's a couple ways. I'm going to show you both. They both use ratios, but one uses them indirectly. You don't see them. And the other is like literally the ratio method. Okay? And it's kind of like using Kepler's third law, whereas the intricate stuff, the details, like big G and the mass of the object, they go away. In this type of a problem, that always happens. Okay? So in your approach to these types of problems, your first step is describe the initial situation, right, the given situation, with an equation. That's your first step. So I need to relate, I should have said with speed v. Right? A shuttle is in orbit around Earth at a distance r and speed v. Sorry about that. So I need an equation that's going to relate the speed v, an orbital distance r, and the mass of the Earth, because that thing's going to change. So I need to figure out a way of mathematically relating the things that are described in the problem, and just write that equation. And I got no numbers to plug into it, but I'm just going to write the equation. All right, well, involving the masses, Newton's law of universal gravitation, right? Newton's second law in this guy isn't going to involve the mass of the Earth. It's just this guy's mass times his acceleration. So I got to use Newton's second law. Got to use Newton's law of universal gravitation in order to get the ME into my equation. So in this first step here, I'm starting with Newton's law of universal gravitation, which is this. Right? Okay, but that doesn't have V, so how am I going to get V into the game here? Centripetal, right? So I am going to use Newton's second law. I know this force is also equal to ma, or mv squared over r. M satellite, that's for the satellite, because the satellite's moving in a circular motion. And as we've already seen, mass of the satellite cancels out. One of the r's cancels out. And I get an equation for the speed, v equals the square root of big G times the mass of the Earth over r. Oh, I think we've seen that before. Hopefully this is becoming second nature, and this is easy now. Like we've set those two equal to each other so often, it's pretty simple. All right, well there, I described speed, which is what I'm concerned with, mass of the Earth, orbital distance. I've got this taken care of, right? I've described the given situation with an equation. And then, so that's dealing with that. And then the situation gets modified. What do I do there? I literally, in the equation, I write a new equation. With these modifications. Meaning, if ME has become 4 times bigger, I replace ME with what? 4 ME. If the radius becomes 3 times bigger, I replace R with 3R. That's it. So I get V equals the square root of G times not ME, but 4 ME divided by, not R, but 3R. Oops. So you write the new equation with the modifications, and then what you're going to want to do is simplify. All right, to simplify, I can use the commutative property and say that I'm just going to rewrite this expression as 4 big G ME over 3R, right? You good with that? And then I'm going to do something, and hopefully you'll understand why. I'm going to rewrite this like this. V equals the square root of 4/3 times the square root of G times the mass of the Earth over 3R. Why did I do that? Oh, by the way, this is a new speed, right? I'm sorry, I made modifications. This is our new speed. Why did I write it like this?
It's a different velocity.
It is a different velocity. But I made sure to write this guy by itself because what is this guy? What? Who said that?
Which part?
Constant?
Was it you? I think it was you. What is this?
The original equation?
It's the original.
Oh, I did say that.
Wait, it's not.
It's the original speed.
It's not. It's divided by 3.
Well,
Oh, I pulled the 3 out. Oops. No, 3 came out. It's there. My bad. Thank you. Thank you.
Yeah, I was about to.
Yeah, it's not the same. No, it is the same though. So that's our initial speed. So what essentially we're doing, we're expressing our new speed as some ratio or some coefficient, some integer value, or not integer, some number times our initial speed. So in this case, and what that means, I can literally plug in V for all this crap here. So I get my new orbital speed is going to be the square root of 4 thirds times my initial speed, times the initial speed. And I can simplify this, right? 2 over the square root of 3 times v. So could I have done that? And it is 2 over the square root of 3, is that a number greater than or less than 1?
Greater than.
It's greater than, right? Yeah. And so am I moving faster or am I moving slower? Faster. Was that obvious? No. It was obvious when all we changed was the mass of the Earth. That was obvious. But if I change that orbital radius as well, it's not so obvious and you actually have to go through this. But our result, if we can interpret it correctly, tells us, right? What is that number? What's 2 divided by square root of 3? 1.15. So that tells us that our new velocity, when I go to this new planet and orbit at this new distance, is going to be 1.15 times the speed that I had when I was orbiting the Earth at a distance r. So it doesn't give us the exact speed, but it tells us how the original speed would be affected. Would it be increased or decreased, or would it stay the same? Does that make sense? That is one approach to this type of problem. I put a few on this assignment just so you guys get to practice for it. There's another approach that actually involves less work. But some students, including me, conceptualize what I just went through a little better. This method is essentially the ratio method, so if you understand what ratios are and how to use them and proportions and all that, then you'll be good to go. But essentially, I can do the same problem. So I say, all right, my first speed is square root of, help me out here. No, the original one.
Oh, it's
GME over R.
I knew that. I just seen if you guys did. All right, that's the new one. All right, that's the first one. The new one, I'm still gonna make the modification. So square root of g times 4me. I'm gonna do the long way. I'm gonna act like I'm doing this from scratch. Or 3r. Simplify the new one to get all the numbers out in front. So new equals essentially the same thing we did, the square root of 4 thirds times the square root of big G times mass of the Earth over R. And then just compute the ratio of these speeds. Because when I do that, if I take the ratio of the old speed to the new speed, well, I have in the numerator the square root of big G mass Earth over R divided by the square root of 4 thirds times the square root of big G me divided by R, which looks gross, but I see what? And so V over the ratio of the speeds is going to simply be 1 over the square root of 4. I'm going to write it like this so my brain can handle it. That will then be the square root of 3 over 2, right? Right? Okay. And then so look, this equals the square root of 3 over 2. So I multiply both sides by V new, and I get V equals, is that different from what we got before? Square root of 3 over 2 times V new. Isn't that different?
Yes.
No.
What did we do wrong?
What happened? Uh-oh. My bad.
What did we do wrong? Oh, it was Alonzo.
Yeah, my bad.
Did I mess up my division here? No, you multiply by reciprocal with square root of 3, or square root of 4 is 2. What did we do last time then?
Wasn't it V new equals,
It was 2
right?
over.
Oh, no, yeah, Jalen's right. Yeah, we solved for V new last time, which means I need to multiply by the reciprocal here. Thank you, Jalen. Oh man, that was going to be embarrassing, and I would not have been able to use this video. Who's my editor? Is that Lexi? Lexi, can you edit this part out of the video, please? Thank you. Yeah, awesome. That doesn't cost extra, does it? So 2 over square root of 3 times, and that is our answer that we got, right? Okay. Thank you, Jalen. Oh man, that was hurting my brain. It's sixth period. I'm starting to shut down. All right. All right. So which way do you want to do it? Very common problems on this assignment. We are going to work on this assignment tomorrow in class. I am going to have you watch some videos tomorrow night for homework so we can get through the rest of this unit pretty quick. They won't be long videos, but I want to get ready to solve some new kind of problems on Friday so that we can get through this and get to my favorite unit of this class probably, which is energy. Working energy. What? Which is a concept not known in Newton's time. So there was no energy considerations in Newton's time.
If I'm holding something above my head like this, am I working at all?
No. Yes, there's biological work being done because of the complex biological things involved in you holding that up. However, you are doing no work on the object.
Yeah.
If you do work on an object, that object's energy will change. So it will either speed up, slow down, or it will raise or lower. Yeah. If that's not happening, then no work is being done on the object. Work can still be done. I can push on the table. I'm not moving the table. But work is done, but that's biological work, and that's way beyond what we do in introductory physics.
Yeah. Ow. That hurt.
See you, Jalen.
Alright, thank you.
Thank you.
Owie.
What's on your shirt, Lexi?
How is it that third period's more eager to leave than this period? I swear.
I never saw it.
What?
I heard it wasn't very good.
I mean, it was okay. I just didn't like the Joker.
You can't. I don't know. There's been some really good Jokers.
I did like
You like who? I mean, I like what's her name? I don't like Harley Quinn. She's pretty. Hi.
Margot Ross.
I sprayed my wrist this morning.
What'd you do that for?
I
You need to stop getting in fights.
I lost my balance on that.
Call Lexi. You have her be your enforcer. She's vicious. Bye, Lexi. Have a good day. Okay. Okay. What's up, Gia?
Hey, people can still see me.
Am I still recording? I'm still
Yeah.
recording.
Wait,
Oh.
Mr. Ben, this is like a 2D depiction
You're in my video now, Taylor.
of how like
Do you give consent to be on YouTube?
Yeah, okay.
Okay.